Jennifer Catto began her career in meteorology with a PhD from the University of Reading on extratropical cyclones, demonstrating how important it is to have a high-resolution model in accurately simulating storm behaviour. She also investigated how greenhouse gas warming scenarios may affect storm tracks into the future. Jennifer then came to Monash in 2010, developing climate models and looking at how much rain comes from atmospheric fronts. Last year she was awarded a DECRA fellowship from the ARC, keeping her here at Monash for another 3 years. During her time in Australia, Jennifer has enjoyed our outdoors, and she recently completed the 7 Peaks Challenge, which means that she rode up all of our alpine peaks, including Mount Hotham and Buller, on a bicycle. With an extensive record of research presentations at conferences around the world and also for general audiences, we're excited to have Jennifer here today. Please welcome her.
Thank you, Kay, and it's good to see so many people here. I hope it's not just for the free pizza. Okay, so the title of my talk is On the Front Line. So I work in the School of Earth, Atmosphere and Environment here, and I am an atmospheric scientist or a climate scientist. So traditionally, people who study the weather would look at short time scales, so things that are happening on a day to a week, for example. And climate scientists would look at long time scale statistics, so looking at the average state of the climate, the average state of the atmosphere over a 30-year period, for example. But what I do, I think, sort of lies right at the interface between those two sort of time and space scales. So I'm looking at the long-term statistics of short-term weather events. Okay. So the particular weather phenomenon I'm interested in is fronts and frontal systems. So I hope you like my little Lego men here. So the term front originally came from the idea of atmospheric air masses battling against each other. So you've got cold air masses from near the pole and warmer air masses from near the equator battling against each other. So this is a map of the annual average temperature over the globe. So this is calculated over all years, so say a 30-year period. So you can see the red colours show warmer temperatures, so in the tropics. This is where we've got our warm air mass. And then the blue colours show the colder air masses. And so you can see that in the mid-latitudes, approximately the latitude that we are, and in the northern hemisphere, approximately where the UK sits, you've got really strong temperature contrasts. So you can see that the lines of constant temperature are quite straight along the latitude bands. But that's because this is calculated, this is the climate, so this is calculated over long periods. On a day-to-day basis, you would see quite large kinks in the temperature contours. So you might have some warm air intruding polewards and some colder air intruding equatorwards. So I'm going to mostly think about the southern hemisphere because that's where we are. And so when you've got this on a day-to-day basis, this is when you end up with the battling between the cold air and the warm air. So what happens when we get this battling? So when we've got colder air moving towards warmer air, so this is a cold front, this is represented by the blue line with the blue triangles, which you can see. So you've got cold air pushing towards warmer air. We know that warm air rises, so the warm air is less dense than the cold air, so as the cold air moves towards it, it undercuts and forces the warm air to rise up. So the moisture in the warm air, as it gets pushed up, the warm air cools, we get condensation, and this is why we get clouds and rain. So when we've got a cold front coming, which affects Melbourne quite often, we expect there to be rainfall. And fortuitously, this is the forecast map that I looked at this morning. And you'll know that we've had a few days of really warm weather. It's very warm today. So we're currently sitting in this region of very warm air. So this is a warm air mass. But pushing up from the Southern Ocean, we've got this cooler air mass. So where these two air masses meet, and we've got the battle occurring, this is where we expect to get the rainfall. So that's shown by the blue colours. So as it turns out, this front itself is actually going to pass a bit further south than Melbourne. So we're not expecting a lot of rainfall, but at some point overnight, the front's going to pass, and we're going to end up with this cold air mass over us. So there's just a little forecast for you. Okay, so it turns out that the rainfall that we get from fronts is very important for various things. So it's really important for agriculture, especially grain growing in Victoria. So a lot of the rain we get during the grain growing season, so during winter, comes from fronts. It's also important for ecosystems and for human health. Obviously, we need water to sustain ourselves. So it's really important to know how the fronts work, how much rainfall they bring, and how this might change in the future with a warming climate. So I've shown you an example of one front that's coming towards Melbourne at the moment. But this is a snapshot from yesterday morning. This is the analysis for the whole of the Southern Hemisphere, so you can see Antarctica in the centre there. So you can see that as well as the front near Australia, there are fronts all over the Southern Hemisphere. So if I want to look at long-term statistics of fronts and how much rainfall they bring, I want to look at all regions and many years. So I don't want to sit looking at plots like this for every day for 30 years. That's just not my idea of fun. So traditionally, studies looking at statistics of fronts have actually done just that. So they choose a small region, say Australia, and they look at the fronts each day for a number of years. So this has been done in small regions, so Australia, the United States of America, for example. But it makes it very difficult to compare the results, because if you showed the same data to two different weather forecasters, for example, they might actually place the fronts in slightly different positions. So we need to make sure that we're using an automated method that does this without any kind of preconceived ideas about where the front should go. It has to be automatic. And it saves us looking through charts and charts and charts. So we use automated programs. So we apply these programs to gridded data sets that we have that are the best estimate of the atmospheric conditions. So every 6 hours for the past 30 years. So that's a lot of information. That's a lot of charts you'd have to look through if you couldn't automate it. So we use these programs, they search through the data and they find locations where you've got these strong temperature contrasts at fronts. Once you find the fronts in the gridded data, you can then match the front information up with information about rainfall. So the information we get about rainfall is mostly from satellite information. So these are some results from the work that I've done looking at the present day climate using observations of the atmosphere. So I found that about 46% of global annual rainfall is linked to fronts, and in the mid-latitudes this rises up to about 68%. So these look like very simple statistics here, but when we published this in 2012, it was really the first time anybody had made an estimate of these numbers. And then we continued and looked at extreme rainfall events and found that up to 90% of all extreme rainfall events can be linked to fronts. So clearly, fronts are very important for rainfall. So we want to know how they might change in the future. So why do we think things might change in the future, and why won't the fronts just stay the same as they currently are? Well, there are two ways that fronts might change in the future. So we know that as you increase carbon dioxide in the atmosphere, you end up with warmer global average temperatures. And a warmer atmosphere can hold more moisture. So this is our sort of present day situation, and on the right is what could happen in the future. So as you've got warmer air, it's going to be moister. As the air rises up, it might produce more precipitation, more rainfall. So this is one way that they might change in the future. The other way is that they might shift their location, so their preferred location, where the fronts move to, you might get more fronts in one place and fewer fronts in another place. So how do we look at what's going to happen in the future? So we use climate models. Now I put these equations up not to scare you, but just to illustrate a point that with climate models, we don't put information about the state of the atmosphere into them. We calculate, the models themselves calculate that. So we don't tell them there are this many fronts and this much rainfall. The models use these equations, which are actually based on fairly simple equations, like Newton's second law of motion, to calculate the winds, the first law of thermodynamics to calculate the temperature, for example. So the climate models solve these equations to tell us what the state of the atmosphere. So we don't just want to calculate this at one point, we want to do it over the whole globe. So we need to break down the globe into manageable chunks. So we have a 3D grid, and at each grid point, this is an example of a grid on the right there. So each grid point, these equations are solved by the climate model. So there are a lot of grid points, and it turns out that a typical model might have 20 billion calculations per 1 day of simulation. So we need very, very large computers to do these calculations. And actually, weather and climate modelling have been the sort of fields of research that have really pushed the development of supercomputers, because we need bigger and bigger computers to do all the calculations we want to do. Anyway, so we use our climate models. First of all, we simulate the present day climate, so with current carbon dioxide estimates. Then I apply the same automated method to that information. So we end up with a gridded data set similar to our observations. I apply the same automated method to find the fronts and link them to rainfall to make sure that the climate models in their calculations are doing the right thing. Then you can run the climate models with increased carbon dioxide and find out what happens in the future. So again, once you've got the future simulation, say from the end of the century, you can then apply these same automated methods to find the fronts and link them to rainfall. But this time, the rainfall is not from satellites, it's from the model itself. So this is just one plot of some recent results. So this is looking at how the fronts might shift in the future. So this is looking at the frequency of fronts in the future compared to the present day. So the blue regions show where there are more fronts likely to be in the future, and the orange regions where there are fewer fronts in the future. So you can see that over the southeast of Australia, the climate models are suggesting that we might actually get more fronts in the future. And in the northern hemisphere especially, it looks like generally there are fewer fronts. Now, how does the rainfall change that come from the fronts? Well, I'm afraid this is still work in progress. This is part of what my DECRA project is about. So you'll have to watch this space. Thank you.